Okay. Hello, everyone. My name is Roman. I'm a Frontend guild lead from Kyiv, and I was talking a lot about React, how to use React, how to use libraries with React, how to build architectures with React, and blah, blah, blah with React for quite a while. But to be honest, I always thought that there is something more important in the world of web development, and it's something that is fundamental for every web developer, and it's something that we keep forgetting. I'm pretty sure that 80% of the information I will talk today will sound familiar for you. Maybe sometimes it will be something like, what are you talking about? We all know this. But I'm also pretty sure that this 20% of information that you maybe forgot, maybe you didn't yet know, can be used, can be useful, and can make an impact for your development. So today we will talk about the platform everyone's using. It's the internet. I will talk to you about how the internet works under the hood. So sit comfortably and listen for me. I have a friend. His name is Server, and he likes to call me client. And each time I need some piece of information, I'm just asking, hey, server, can you please give me that piece of data? And he responds like, yeah, please, sure, take it. Or no, sorry, dude, not today. I'm pretty sure that it's not happening simultaneously. And I call it, oh, okay, yeah, it's asynchronous, of course. It can be difficult because we're not in the same room every day. He can be in the other part of the building, in another city, country, and even continent. He can be on the other part of the world, and it can be unreliable. And I know this, but this unreliability and asynchronous work is something that is far more interesting than it can sound. The travel of this request can be difficult. It can be a lot of troubles. Basically, it's a tale with good and bad, evil characters. So close your eyes. Imagine you're in a wonderland, and I will tell you a tale of one request. First of all, let's go to the very basics. It's the standard OSI model that describes how our protocols are aligned and work together. When my friend server located in the other part of the world, I would like to negotiate, to discuss with him how we can talk to each other. I could develop each negotiation for every time, but we can discuss up front and split it into different levels, so we will reuse most of them. First level is physicals, how signals are traveling through some medium, for example, through radio in Wi-Fi, or cable, or through light in optical wires. Then, when we know how to use our signals, we should discuss how we will pass data through these signals between two directly connected devices. For example, your laptop and mobile. This is data link, for example, Ethernet protocol. Then, when we know how to pass data from one device to another, let's talk how to pass data from one device to another that is not connected directly, that can be in the other part of the world. This is where the internet starts. This network level protocols, for example, IPv4 or version 6. Then, on top of this, we can develop transport layer protocols. The most common one is TCP, Transmission Control Protocol, that is used maybe 99% of time. That gives us the abstraction of reliable transfer over the unreliable network. Then, when we have all these guarantees we need, we can think about some session details that is for one particular connection. For example, encryption, authentication, SSL, TLS. Then presentation, how do we encode, decode our data? We will encode, decode text and images, videos differently. And only then, on top of all these protocols, we will have the application-level protocols that everyone is dealing each day for quite a while. It's HTTP, for example. It's only the top of the iceberg. It describes how you use all this infrastructure below. So let's go to your favorite browser, type these numbers, and surprise, surprise, we will get Wix.com site. You can notice we will have the same as we will just type Wix.com, push enter. What happens is a totally simple travel request. We are requesting something from server directly. The number you saw, it's IPv4 address that describes where our server is located, so our browser knows how to navigate to this address. And the server responds with simple HTML with our site. Okay, but what you could also find that passing these numbers, memoizing is ask someone to navigate to these numbers is totally inconvenient at all. So Internet developed domain name system. It's just a catalog where your browser will go and ask, hey, where's Wix.com located? It will answer with these numbers, and your browser will navigate there. So before it will go to our servers, it should go to DNS servers. There are lots of them. They are well known, and maybe the first of them will be even just local. But let's go a bit further. It was IP address. It's how just to find our servers. Then HTTP utilizes TCP. TCP is the abstraction that gives us reliable data transfer over the unreliable network, because packets can be lost, they can be corrupted, and so on. And TCP guarantees us that they will be delivered to the order we sent, and so on. Our data is split into small packets because you will send all the gigabyte of video request in one request. It can in one packet. We will lose all the gigabyte. It's inconvenient, so we will split it into small packets, and we'll do something like small request response on the transport layer protocol. To use TCP, we need to connect, to have the connection ready. And this is a problem. To establish the TCP connection, we need to do a lot. Our operation system. We need to do three-way handshake. It's like intelligence here. We push one packet with all the meta information. The server will respond that, oh, okay, he gets this. He proposed to use some sub protocols and so on. Then we will respond with data. This takes to go there and back. The problem is the latency. We have huge bandwidths between our devices, but we cannot do anything with the latency. How fast signals are traveling? Well, it's more or less speed of light. If you think that speed of light is huge, no, it's not. Because in a modern world, you want to everything to happen in milliseconds, but light will travel for like 50, 100 milliseconds there and back between continents. And to establish the connection is hundreds of milliseconds. Then what will happen is a slow start. We don't know how big the bandwidth between us, how good the network is, and so on. So we need to check it. And we will start slow and increase the usage of the bandwidth with time. And doesn't matter if you have a gigabit connection between you when you start. You're using a small amount of this bandwidth. So even small pictures with hundreds of kilobytes, megabyte, can be downloaded with a few round trips of latency. And latency is expensive. So we need to think about this. We need to reuse it, and so on. Then, when we know the problems with TCP itself, mostly in a modern world, we want to have some protection. We're using HTTPS, not just HTTP. What is HTTPS? It's the same HTTP, but it works on top of one more layer. It's security layer, TLS. What TLS provides us is basically 3 features. You can use them separately, but mostly you don't. You use them in as one. And the first one is authentication, because we want to be sure that the server we're talking with is what we want. If we were given our payment data to Wix.com, I would love to be sure that it's Wix.com, not someone that tells that it's Wix.com. How it's done? We have some well-known services, certificate authorities that like every browser, every operating system trusts. For example, Google. Yeah. And when we want to your browser to be assured that we are Wix.com, we will ask this Google to sign that, yeah, it's who we are. And then, having this public key of Google, we can check if it's really Wix.com. We don't want this to be monopolized, so this is not just one service. We can have a huge chain of certificate authorities. Wix.com will sign to, for example, Google will sign to Wix.com. Wix.com will be able to sign certificates for our sites and so on. This chain can be as huge as we want, but there are some problems. First of all these negotiations are happening while on the first stages. Remember this slow start. It means that if this chain will be big enough, it won't fit into the initial window size, and we will have additional round trips of latency. And latency is expensive, and we cannot do anything with this, so we should avoid this. Plus, sometimes our certificates are getting revoked. And how browser knows that the certificate is revoked? It needs to make another request to the Certificate Authorities Center, asking if this certificate is still working, if it hasn't been revoked, and if you will have 5 levels of certificate authorities in your chain, it means that it can ask each of them. And you cannot do anything with this, so do it as short as you can. Then, when we know who we're talking with, we would like to encrypt the data. I don't want someone to stay in the middle and just write down my payment data. So I would like to encrypt this. How do I do this? It's done mostly with asymmetric cryptography. Yeah, browser and server has some shared secret. When I'm passing some data, I can encrypt this. For example, I want to pass 10. I will add 5, and the server will subscribe 5. That's easy. But how do we exchange this common secret over the network while everyone can see it? Well, this is where we use asymmetric cryptography. The most simple one you can imagine. We will just generate private public key. We will send public key. It's called public because everyone can see this. The man in the middle will receive my public key. My browser will receive my public key. Then I will generate my shared secret. Will encrypt this and push into server. And that's what's interesting, because in asymmetric cryptography, these public and private keys have the ability to encrypt and decrypt each other. So something that is encrypted with public key can be decrypted only with private, and vice versa. Having one key allows me to just to encrypt, but not to decrypt. This means that I can generate these 5 will push it to my server. The man in the middle will know my public key and 42, but he don't know what to do with this. But my server has a private key, and he can decrypt it, and now we have this common secret. Okay. The third part of TLS is data integrity. We don't want someone to corrupt our data in the middle. We want to make sure if someone is sending my data, that no one in the middle will take this packet and will replace it with its own. Basically, it's just like a checksum signed by our keys. And now we can talk about HTTP finally. So HTTP is an application-level protocol that utilizes all the stuff I talked before. And the first HTTP was absolutely simple. Nothing between. It was designed to be simple. It would make it so common that everyone could use it and implement. It was just one-line request, no headers, no methods, nothing. Just get this URL, and the server would respond to you with some data and close the connection. That's all. But open and closing connection is expensive, as you know, and just requesting something from some endpoint is not enough. So it developed into HTTP 1.1, where we have the reusage of TCP connections. This the number one feature, because this connection keep alive allows us to reuse the same TCP connection, and first request would be slow, but all the other requests will work just fine over the already established connection. We also added some metadata, headers, methods, some caching, hypermedia. Yeah, it's hypertext transfer protocol, but in reality, HTTP is used to transfer video, photo, binary data, whatever. In a modern world, you can transfer anything with HTTP. But HTTP 1.1 wasn't enough as well. In a modern world, we would like to go further, and we developed HTTP 2. What is HTTP 2? Basically, like number one feature in HTTP 2 is request multiplexing. What happened in HTTP 1? One request could travel through one TCP connection. That's all. That means that if we would like to have few HTTP in parallel, we need to establish different TCP connections. That's expensive. Then you cannot establish all of them, like 100 TCP connections. You're limited, for example, with like 5, 6, 7 TCP connections for different browsers. And you cannot do a few requests through one TCP connection. You need to wait until your server will respond to you. It will finish this response, and only after this you can use the same connection to make another HTTP request. And this is called head-of-line blocking. If you need to make 100 requests, you need to wait until the first 5 will finish, and then make another 5, and so on. So developers decided to do like optimization, best practices that you could know by now. For example, domain sharding. Yeah, browser is limiting you for 5 connections. Okay, I will do 10 subdomains, and it will establish 50 TCP connections. Or bundling everything into sprites or big files where that will be requested in one request. That's all good, but you don't need it in HTTP 2. In HTTP 2, all the requests are done in one TCP connection. So you don't need to open a lot of TCP connections, only one. And you can do like 100 requests through one TCP connection, and it's great. You still have head-of-line blocking on TCP level, because if packets are lost, you need to retransmit it, and so on, and you need to wait until you retransmit them, and only then go further. So you still have this, but on TCP level, and you don't face it a lot. But on HTTP level, you don't have head-of-line blocking anymore. You don't need domain sharding. You don't really need bundling and spriting because now you can use like lazy loading, code splitting. You can request 100 images in one TCP connection, and they will work just fine. And you won't download all 100 images for all your site, only like 10 that you need right now, and it will be much better. So like forget about this bundling and spriting and so on. We also would like to reduce our overhead with all these requests. It's headers compression. For standard headers, you have like standard codes, and it's not transferred as a huge string, just some codes, and it's cached. And all this done now in binary framing. What is interesting, HTTP 2 is the same for application level. You can use the same requests from browser, from your server applications. So API stays the same. It's called major version 2 because it has different protocol under the hood. It's not a text protocol anymore. Now it has binary framing. And what is interesting is server push. Now it's two sides. Now it's not just you who can ask server. It's server who can gives data to you, even before you will ask for this. It's not implemented in a lot of server solutions. It's not supported in some of the browsers yet, but it's in a standard. And sooner or later, we will have this. And this is pretty interesting stuff when you know upfront that your client will need some information. For example, it loads index.html, and you know that it will ask you for index.js, index CSS, and blah, blah, blah. You can just push it to him, and when he will ask, it will be already in its cache. That's great optimization that can be done. What's another application level protocol that works on top of TCP is WebSockets. WebSockets, you know, everyone knows about WebSockets, I believe. It's duplex communication where you can send data to server, server could send data to you, and so on. There are a few misconceptions that I constantly hear, for example, on our interviews. First of them, that WebSockets works on top of HTTP. That's not right. WebSockets are the separate standard that works on top of TCP. We have the same like WebSocket Secure working on top of TLS. It doesn't require HTTP at all. HTTP required only for a handshake to establish the WebSocket connection. Theoretically, it can be established with any other protocol, but in practice, it's implemented only in HTTP. So you need HTTP to establish the connection, but afterwards, it works separately. If you will try to push WebSockets to our infrastructure, you will understand this. If it would work on top of HTTP, it would work. It's not. Okay. And the second main part is WebSockets works on top of TCP. This means that it's guaranteed by transport level protocol that you will get all the information and you will get in the same order you ask this and so on. So stop talking about it's unreliable or something like this, or it's not guaranteed an order. Order is guaranteed and the delivery is guaranteed as far as you have the connection between you at all. What's the standards most or some of you is not using every day is UDP. UDP is the transport layer protocol as well as TCP. And it's used when you don't need all these guarantees. Yeah, having the guarantees that you will have all the data sent, received in the same order and so on, that's good. but sometimes you don't need it. And there's where UDP comes. You just send all the data you need to your client or to your server, and some of the packets will be lost forever. No one cares. Some of packets will be delivered in a different order. Okay, no one cares as well. It just works on top of IP, and you send this data and so on. Some will come, some won't. And for some applications, that's okay. For example, the WebRTC protocol, the WebRTC API that's implemented in all major browsers works on top of UDP, and it is the only way to establish peer-to-peer connection between browsers. From the beginning, internet was symmetric. There was no restriction that is a server, this is a client. You can communicate between any node in your network. Now it's not quite like this. By de facto, internet evolved in the client-server paradigm. So browsers are clients. They are meant just to request, servers to respond. That's all. But what if I would like to communicate to another browser? I can do it with WebRTC protocol that runs on top of UDP. And theoretically, I can do real-time video, chats, audio, sending files from one browser to another without any servers and so on. In practice, it's a bit different. In practice, it's you will need server at least to establish this connection because we had some problems. But let's talk about this. Let's go back to our HTTP and we'll write some numbers. We will navigate. We will go to 404 page. Why? Because I've got to the server. This is GitHub pages server. I wanted to find some site there, but it didn't know what to respond because we have trillions of sites all over the world and only 4 billion addresses. Yeah, it's a small amount. Someone thought that it's enough, but it's not. For servers, it's okay. I can look for its headers, and when I come to my server, I will ask, oh, hey, give me this site, and server will respond me with this site. That's okay. But where the shit hits the fan, it's when your server needs to respond to you. But who's you? You need the IP address as well. There are billions of people around the world. Each of you have few devices and so on. We have a lot of devices, much more than these addresses. So it was solved with so-called NATs, network address translators. For example, you have some IP address, but each application on your device has not just address, it has ports. You can imagine like a building and the apartments in this building. So your application will communicate to the network and it will get the response back. It looks like this. In practice, to communicate to internet, you need some globally unique IP address. You won't have it, but your provider will. It will have the IP address like this. And it will assign you some local IP address. It will look something like this. We have predefined ranges for local IP addresses. So your devices that are connected to the same Wi-Fi network will have different local IP address, but for the all other world, it will look as this. But network address translator for each outcoming request will assign you some port, for example this, and it will map this port to this local IP address with this port. This sounds okay, but there are obvious problems. First of all, now you don't know your own address. You cannot communicate it directly. Okay, this can be solved. This calls I stun and turn. I will talk about this a bit. So if you would like to establish peer-to-peer connection, what you can do, you can put some server and make two requests from two different browsers, asking how my address looks from the outside. And it will give you how your address and port looks from outside. It's what network address translator aside for you. Now you know these addresses and you can communicate between each other. That's fine. But it's not always like this. Sometimes you have troubles. For example, NAT has limited amount of ports. This means that sometimes it needs to kill some connections or reassign it and so on. So it's not a viable solution for long-living connections. Then some NATs do even better job. Yeah, it will assign the port not only for your application. Yeah, it not just will map like 3000 to 2345, but it will assign for each outcoming connection, and your server will see one port, but for the other browser it will be closed. So the only way to establish peer-to-peer connection is to do it with turn. That is basically not a peer-to-peer connection at all. Well, stun is a session traverse using for NAT. Turn is like relay for NATs. Basically, your traffic is routed through some centralized server, and it's not peer-to-peer connection at all. And you have no way to establish this peer-to-peer connection because you're hidden by the net that doesn't allow this. And there are a lot of different other items in internet infrastructure that doesn't allow this. So this is a problem. And one of ways to solve this problem was like the new standard of internet, IPv6. There are a few different features. For example, it makes routing a bit easier and so on. But the main feature of IPv6 is it's bigger. When Internet Protocol version 4 was developed, it was obvious that 4 billion addresses is enough. Yeah? Who will use this Internet? But in real life, it's not. So IPv6 allows you addresses like this. It's 128 bytes, not 32 like bits. Sorry, like IPv4, and it allows a tremendous amount of addresses that will be enough for all the devices, people, and like IoT devices and so on. The problem with IPv6 is it's already 20 years from now, and it's not deployed everywhere still. So for you who tried to migrate into a newer version of your framework in your application, you can try to imagine how hard it is to deploy a new version of internet. Yeah? It took 20 years, and we're not there yet. For example, this is an IP address of Google. You know why it's not Wix? Because I know one company that is 5% of the internet, that is 150 million users, that's not using IPv6. And we can understand this because it's not a huge business impact at all. And this is why it's getting time to deploy it, and for the next 10, 20 years, we will live in a world where the adoption of IPv6 is not full. It will work in parallel 4 and 6 standard. and they are not interoperable. So this is a lot of problems. And by the way, I couldn't even make a screenshot of Google with this address because, for example, in Ukraine, the adoption of IPv6 is less than 1%. In Israel, it's 4%. 4% people can use IPv6 standard on their devices for their providers. For example, in US, it's around 50%. In India, it's #1. It's almost 70% of adoption of IPv6. So for India market, it can be crucial, for example. What's interesting is what can await us in the future of HTTP. HTTP 2 is already here. We can use it for years from now. Just few of the features are not fully supported in every major server and browser. But HTTP 3 is something that can be our future, and is developed. It was developed originally in Google, just like HTTP 2. Yeah, and it's totally different. HTTP 0.9, 1, and 2 worked on top of TCP. It was to make our life easier. HTTP 3 will work on top of UDP standard, and it will allow us to get rid of head-of-line blocking in a transport layer protocol. It will allow us to reuse sessions. What happens now when we're switching from, we're on a mobile device, and we're on a Wi-Fi network, and we're switching into 3G, LTE network, mobile network. We're losing everything. We need to reestablish all the connections, all the sessions, and so on. But in HTTP 3, it will be like a part of a standard carrying the session ID and reuse it when you're switching the networks. Some like troubles that I was describing you in this presentation and some like optimization best practices may not be actual in the next like 5 years. It can change. So what I want you to understand from this small tale, is that everything's changing constantly. What was considered the best practices 3 years ago, like ultimate best practices, it's not good practices at all right now. It's changed. And in 5 years from now, it can change. So take a look at the APIs you have, take a look at the protocols, take a look at what you can do right now, what is available. It's like WebRTC or something like this. We couldn't imagine this like 5 years ago. But now it's there. We can use it easily. On a hackathon, we had at least 3 teams in Kyiv that were developing something with WebRTC. It's already here. So take a look at this and ask yourself every time about if these best practices are still best practices or no, and so on. The end.